Hi, everybody. Today we are going to hit rock bottom, just like it was last night, and we are going to talk about the absolute bottom of sort of looking at how computers work. And then actually the next lecture tomorrow, we're going to go pop right back up to the top, kind of where we started at the beginning of the course, and we're going to sort of build up from there, talking about modern methods of getting better performance out of computers. But down here at the bottom, at the molecules and the atoms and the charge carriers, we're going to talk about the physics that's involved in actually doing computation itself. So remember yesterday we talked about when you want to communicate a bit from one place to the other, that communication involves sending energy from one place to the other. And now we're going to ask ourselves the question of, once the bit is received and you want to store it as a memory value, how do you actually store it? And we'll see that that involves energy as well. And then in terms of computation of doing ands and ors and things like that, that involves some energetics with some non-intuitive answers. So let's get started. Just remembering again the essence of information transmission when a wave is propagated along a wire or in the air or however you want to do it, it's energy that is transferred from one side to the other, from the transmitter to the receiver. And that is the form that the information itself is taking, is physical energy. And you remember, again, the sort of simple memory element, the set, reset, flip-flop, and that with two high values on its inputs, that is the same circuit over there with the NAND gates as this one over here is with the inverters, which is really the same circuit as this buffer with just some positive feedback around it, and that buffer can in fact exist stably in one of two states. One is the high state, and then the other one is the low state. And then remember we talked a bit about this curious metastable state in the beginning. But let me ask you an interesting question. I saw some stuff from the recitation on the board here, which leads me to think that maybe you actually could answer this question yes. But as far as what I've taught you so far, have I taught you enough to really understand how it is that a logic element like this, with feedback around it, remembers anything? So sure, you could say, yeah, if there's a modestly high voltage here, because the logic element itself improves the quality of the signal, it'll make a higher voltage over here. And that'll go around and around and around until we sort of get stuck at a voltage which is nice and high, and it'll stick there. But let me ask you a sort of philosophical question. Why can't this device, which is latched in the high state, suddenly decide, you know what? I've changed my mind. I'm going to latch in the low state. Have we really explained, other than saying that instantaneously that this takes some voltage over here and transfers it to a voltage over there, have we really explained how this thing remembers? And I'm hoping, except for the recitation yesterday where I saw some hints that you actually went into how this works, that you're still a little bit puzzled by why it is that a device like this, I hope you're puzzled, because it should be a little bit strange that this doesn't instantaneously change from high to low. Okay. Now, let me ask a sort of stupid question. Why is it that that chair over there doesn't suddenly move to over here? Why is it that when you close your eyes and open them again, that chair hasn't moved? What is it about the chair that makes it?
There's no force pushing it into confirmation.
Okay. There's no force pushing on it. Let me ask a question. If it didn't weigh anything, if its mass was 0, what would it act like? Well, okay, its mass is not quite 0. Its mass is, you know, a billionth of a gram. Now what's it act like? What happens if a little breeze comes by? Whoosh, right? Because, you know, F equals ma, right? And to accelerate something, you need a force which is proportional to how much you want to accelerate it and how big the mass is. And if the mass is very, very small, then the amount of force it would need to accelerate the chair one way or the other would be very, very small. And if the mass was 0, how much force would it take to move that chair from there to here? 0. Okay. And how fast would it move? Incredibly fast, right? Instantaneously. So there's this kind of amazing thing going on here, that it's the mass of the chair that helps it remember where it is. And it's our mass that helps us remember where we are. Well, okay, that's kind of a... And why am I standing here and I'm not over there? Because I'm heavy. Okay? Because it doesn't just take an incredibly slight breeze to push me over to that side over there. So what's going on here that's comparable? Where's the mass in this system? Well, we haven't talked about any mass in this system. We've only kind of talked about forces, that voltage leads to voltage, which goes back around on the wire. But in fact, there is mass in the system. There is. And so if you take a look at two of these buffers, and it works for one as well, but it's more beautiful to look at two that are like this, coupled around in a circle, where it's really stored, and again, I saw this on the board from the recitation yesterday, which is really good, is in fact that every electronic device has some resistance in the output, and every electronic device has some capacitance in the input. And this RC delay, as it's called, resistive capacitive delay, limits the speed of the propagation going around the loop. And in particular, the point I want to get across is that this capacitor is kind of the equivalent of the mass, how heavy the circuit is, how much current it takes coming out of this wire here to get this thing to move its voltage up or down. Okay? Thinking hydraulically, this is the bathtub, and this is how thin the pipe is going to fill up the bathtub. Okay? And even though the city water wants to fill it up instantaneously, the fact that the pipe has a finite size and the bathtub is non-zero in its size as well means it's going to take some time for that to happen. And once it has happened, so let's say this is one bathtub and it's full, and it causes the water to turn on to fill up this bathtub here, which then causes the water to turn on to fill up this bathtub. So now we have two tubs of water and a system that's measuring the levels of each of the tubs of water and filling up the other tubs in proportion to the level, okay, except that when the level's real high, they kind of run out of water to fill up. Okay? Now, what's stopping the tubs suddenly from becoming empty? What's stopping this circuit from suddenly going from all highs to a set of lows? The water. There's all this water in these tubs, and it takes time to get rid of it, and the water is not suddenly going to disappear. It's the mass in the system, the mass in that chair that suddenly stops it from moving from one place to the other. And the water in the tub is actually storing some potential energy in the mass being lifted up a certain amount in the water. That's why if you hook the hose up to the tub at the bottom of the tub and a little fan, you could get the water to make the fan spin and get power out of the fact that the tub was filled up with water. And similarly, you learned in recitation yesterday that there's 1/2 CV squared energy stored in the capacitors in this circuit, where V is the voltage. So in fact, what's going on in this feedback circuit here is that there's capacitance. The capacitance has stored energy. And that energy is the bit that is being stored. And what these circuits are doing is nothing more than refreshing that bit. They're constantly reading the bit, seeing if it's a high or a low. And if it's a high, even if it degrades a little bit, it restores it with a high that is of better quality than what it read. Exactly the same lesson that when we talked about how dynamic random access memory worked. Do you remember? That was a matrix of little caps just like this one here. And we said every thousandth of a second, the hardware needs to read out the value of the charge that's stored here in this little tub here, and then write it back with higher quality than what it read, because it can leak out after a little while. Circuits like this work exactly the same way, except the refresh is happening continuously, all of the time. So all of the time, those two capacitors there are being read, having their quality improved, and being written over and over and over again. And that's what keeps the bit stored. It's the capacitance, not the feedback. The feedback restores it and stops it from leaking away, but the actual storage is happening here and here. And if we only had one of these things, it would be happening right there, which would be fine too.
Where is the energy coming in that restores it all the time?
Ah, there is a power supply connected to these devices. Perhaps if you use a standard off-the-shelf device, it's 5 volts and ground here. And what this thing does is it senses a voltage here, And in general, if this voltage is, if it's +5 in ground, if the voltage here is more than halfway up, more than 2.5 volts, it connects this output to +5 volts. And if it's less than 2.5 volts, it connects it to ground. In other words, it has a transfer curve that tries to look like that. Now, it's non-ideal, so it has a little bit of a slope to it, kind of like this, which is, again, that S-shaped transfer curve between V in and V out that we talked about before, but it does it by connecting it to the power supply of the computer. Okay, but remember, this part of it is stateless. It has no state. It can't remember anything. All it can do is improve the quality of what is stored here. The storage is actually happening inside of here. That's where the bit is stored. That's where it exists. In general, there are inductors, which have an inductance L, capacitors, which have a capacitance C, resistors, which have a resistance R, and most circuits, most simple circuits that we have can be described in terms of these things, plus various gain elements like transistors that look like this. That's a field effect transistor, and some of you from the old days may remember junction transistors that look like that. Okay. These devices, from here down, in their ideal form, have no memory. Okay, they just have relationships that, for instance, if the voltage is high here, the switch is closed. If the voltage is low, the switch is open. You remember that. This, the voltage across it is proportional to the current that's going through it times the resistance of the device. These devices over here, however, can remember things. They have state. They have memory. And in particular, this stores charge, and this stores a magnetic field, which says that whatever the current used to be, I want to keep the current the same. This one stores charge so that whatever the voltage used to be, I want to keep the voltage the same. And so this is where the memory is. And this is where sort of the stateless functions are. Very much an electrical analog to thinking about combinational logic and registers. Remember, we built FSMs out of two parts. One part that had the ability to do a function, and the other part that had the ability to remember something. Well, in the circuit domain, these are the parts that can remember things, and these are the parts that can do the functions. Okay. Now, I think I've convinced you that memory has to reside in elements that store energy. I also think I've convinced you that the way the elements work is that they try to resist change. Anything that stores energy tries to resist change. The bathtub full of water does not want to change its level. You have to add a lot of water and wait a while before the level of the bathtub will change. Okay? Anything with energy is like that. The same thing is true here in terms of the magnetic field. It doesn't want to change. What that means is that if you do want to change it, it's going to take some time. I cannot instantaneously change the charge on a capacitor without having a current which is infinitely big pulling the charge in or out. I cannot change the position of that chair instantaneously to here without using a force which is infinitely big, because remember, F equals ma, right? If I want to accelerate that thing in 0 time to over here, I need to do it instantaneously, and I need an incredibly large force. If I want a car that's very fast, right, so I can get from here to there very quickly, I need an engine which is very big, and I need to use a lot of force in order to try to accelerate it. And even then, can I make it from here to there in 0 time? No. Okay, it will always take non-zero time. And so therefore, because memory and bits that exist stored in the machine take energy, it will always be the case, and this is also a kind of a wild notion, that transmitting information takes time. There is always going to be a delay in changing these bits from a 0 to a 1 or a 1 to a 0. And again, the way to think about this, and I know this will take a little while to get, is that these ideas of time delay, of energy, and state are all kind of intimately coupled with each other, and you can't have one without the other. There is an alternate way to view how a circuit like this holds on to a memory value. So let's say it's high on both ends. And I said to you, well, it's hard to know why it shouldn't suddenly change from a high to a low. Well, maybe it's not quite as hard to understand if I say this wire has some time delay associated with it, d. Well, in that case, this high takes a while to get around to over here. And by the time it gets around to over here, and let's say that it now gets here, this thing is going to reinforce it and send the new value, which itself will take a long time. And you can imagine all the little highs in here waiting in line as they're slowly shifting out towards here. And then you can say to yourself, oh yeah, I understand how this thing works. It's a sort of stateless, instantaneous voltage restorer device up here, which makes the signal better than it used to be, coupled with a time delay over here. And that time delay is where the bit is held, which kind of makes sense, right? If I have a bunch of people, right, and I have a system where, you know, you're holding your hand up, right, and a bunch of people are standing in line, and people get tired, so they slowly drop their hand. But as they circle around this line here, there's a man over here that says, well, if your hand is more than halfway up, I'll push your hand the rest of the way up and put you back in the end of the line. And so there's a bunch of folks in line here, their hands slowly going down, and then they get their hands picked up again. I can understand where the state of the machine is being held. It's being held right here in the queue of the people kind of with their hands slowly going down. It's certainly not being held by the guy that's pushing up, because he's just as happy if the hand is down here to push it down. Okay, so the memory's not here, it's in here. But I hope that I've convinced you that time delay cannot be done without energy. That really what's going on is that there's energy stored in every one of these bits that's propagating along this wire here. In fact, the energy, if these were people with their hands up, is happening in the, you know, the potential energy of holding your mass of your hand up against the gravitational field of the Earth trying to pull it down. And so that's the energy in the system. That's where it's being stored. And it takes time to change that from high to low, okay? And time to make it through the propagation here. So time delay being non-zero, energy being required in the system in order to have memory are three extremely intimately coupled things. In fact, they all really say the same thing, even though you think about them as three different things. So,
how are inductors used, coils used?
So typically the inductances on a chip are not big enough to actually make use of them for memory. And so they're typically not used. It's also the case that an inductor is a much less ideal device when you build it out of wire than a capacitor is when you do the same thing. So in a capacitor, you have to worry about the fact that, you know, you put some charge here, right, like we talked about the other day, and some of it will leak off because the insulation isn't perfect, okay? It turns out that you can make pretty good capacitors on an integrated circuit. An inductor, you put current in here, and a magnetic field forms, right? But the magnetic field, that doesn't want to change, but it will change due to the resistance of the wires that are here. In other words, keeping the current the same. Here you want the resistance to be 0. Here you want the resistance to be infinite, okay? And it turns out it's easier to make an insulator that's closer to this than it is to make a conductor that's closer to 0. And so for that reason, these are usually not used as memory elements because they don't store the memory for as long.
How does the inductor store?
So let me see the right way to think about this. Okay, we understand how this is like a bathtub, right? How you pour water in and it stores it in there. This is like, have you guys ever in your house turned off the faucet and the whole house goes bang? Anybody ever had that happen when you turn the faucet off? It's called water hammer, right? And what that is the fact that the momentum of the water in the pipes means that the velocity of the water doesn't want to change. You've got all this weight and it's barreling along the pipes, and all of a sudden you close the valve, bang, and all of a sudden this big wave of water is going bang, 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 you know, just whacks up against the wall. The idea is kind of the same here too. The charge carriers are going in a overall direction around a coil like this. That creates a magnetic field, okay, around the thing. If you have a wire that goes like this, the field kind of goes around in a circle like that. And then if you coil it up, you get a bigger field, okay? I'm going to leave this all to Sam's son, but to Sam Jr. But as a result, the magnetic field itself doesn't want to change either. And so when you try to slow down the amount of current that goes in this thing, it actually develops a compensating voltage across the coil, which tries to keep the current going more. And so I don't know how many of you have played with, let's see, the way a spark coil in a car used to work is that there are these set, in the old days, a set of points that would short the coil across the battery of the car, and the points would open. And the coil would get so upset about this, that you're trying to change the current, that you get this incredibly high voltage on that coil, which would cause the spark to happen. And so that's basically working the same way. It's remembering the fact that it used to have current going through it. But because in order to store that information forever, you need a wire with zero resistance, and that's so hard to do, compared to an insulator with very high resistance, which is much easier to do. It turns out these are used much more to store things than those are. Yeah?
You've accounted for physically for the propagation delay. The contamination delay is the same physical phenomenon?
It's the same physical phenomena, but it's a measure of how fast the junk gets through. But it's basically the very same thing. Right? Absolutely right. Okay. So, you did this in recitation, but let's go over it again. Let's say that we're going to store a bit on a capacitor. And the way we're going to do it is that we're going to switch a switch over here between a high voltage and ground. Well, when we connect it to the high voltage, charge goes into the capacitor and fills it up until the voltage on the capacitor is V. It turns out, regardless of how slowly or how fast that process happens, the amount of energy that is stored on the capacitor when it has V volts on it is 1/2 CV squared, where C is a measure of how much capacitance you have. What's interesting is that, again, regardless of how fast you charge it up, how big that resistor is, the exact same amount of energy that goes into the capacitor is also dissipated, is wasted in the resistor on the way. So here's a neat way to think about it. If you have a water supply to your house at 50 psi, right, which is a typical pressure of the water that comes into your house, and you have, let's say, 1/2-inch piping going from the water main up to your tub, and you open up the valve, right, and you fill up your tub, and your tub fills up a certain amount, and then you turn off the water, you can measure how much potential energy is in the water, the mass of the water in the tub, okay? And you'll come out with a certain number of joules of energy. Well, it turns out that that exact same number of joules of energy was dissipated in the form of heat of the water going through the 1/2-inch pipe going to the tub. It's kind of a wild thing, okay? If you had thicker pipes, you might think that the amount that was dissipated is less. But in fact, it is exactly the same, because the speed of the water going through the pipes would be higher in that case. And it turns out when you do the math on this thing, which again I'll leave to Sam's son, the math turns out to be that the integral of the energy dissipated in a circuit charging a capacitor is equal to the energy that is stored in the capacitor at the end. Okay? So now where does all that heat go? It actually warms the water up just a little bit before it goes into your tub. So
where is the heat generated? Friction?
it's just friction, yeah, the friction of the water going through the pipes.
With the wall?
With the wall of the pipes, and then actually most of it is through the valve. When you turn the valve isn't open the whole way. And so there's a little friction of the water trying to go through the valve. Yeah. So here, the heat is dissipated in the resistor, because any current that's going through the resistor here dissipates power with a law which is I squared R. That's the amount of heat loss, of power loss that's going through the resistor. So charging the capacitor up from a voltage source like this means that you do fill this guy up with 1/2 CV squared, but you also, in the process, dissipate 1/2 CV squared of energy in heat in the resistor trying to charge it up. And then when you go and you switch this switch from V to ground, then what happens? Then the 1/2 CV squared, which was in here, goes into ground. But where does the energy go? The answer is it's dissipated in this R right over here. And so this R loses 1/2 CV squared when you charge it up. And then when you put it to ground, the 1/2 CV squared that's in here goes back into the R and is dissipated as heat.
In recitation yesterday, we saw that power consumption was related to the, among other things, the width and the length of the resistor. So, or of the transistor, which is essentially the resistor in this model, right? Because that's where the resistance occurs.
It is as well. It is if. What's the right way to say this here? It is and it isn't. Okay. If the capacitor doesn't change, the value of this resistor doesn't matter. Okay, and I'm not sure exactly what you did in recitation, but if you have a voltage across a resistor, then the lower the resistance, the more power is dissipated. If you have a current in the resistor, the higher the resistance, the more power is dissipated. But the current that goes into here looks something like this. Okay, let's say that the capacitor was initially uncharged at 0 volts. Okay? And then we have a resistor and a switch and a power supply at 5 volts. Right? And we suddenly close the switch. What happens is that when we first close it, the voltage across the resistor is 5 volts. And so if this is R here, we'll get 5 divided by R current going into the capacitor. So we start out with no current going in, we close the switch, and we get a current like this. But very quickly, this thing begins to fill up, right? And as this thing fills up, and the voltage, as it fills up, kind of looks like this, where this is 5 volts here, the amount of current that goes in starts to go down and looks like that. And the reason is that as this thing fills up, the voltage across the resistor goes down, and the amount of current that you end up getting to fill it up goes down. Okay, so this is the I, the current going into the capacitor over here.
Can you step back a little bit, please? Thank you.
And I'll go to the other side. So that's what the current looks like versus time. And this is what the voltage on the capacitor looks like versus time. Starts out very high, and then as the capacitor fills up, it goes down to 0. Okay? There's a much easier way for everybody to see this. Okay? Let's say that here's the ocean, right? And it's so tall. And you've built a very special sand castle with a little door down here at the bottom. Okay? And you've built it, and you've dug in the sand out to here, right? Well, when you first open the door, the water's going to flow in here very fast. Right? And then the water will start to go up, and the higher the water gets, the less the difference is in between these, and so the slower the water is going to go until finally you get to the top and the water stops going. The rate of the water flow here to equalize these two things will follow a pattern that looks like this. Start out very high, then exponentially go down to 0. Okay? Now, the potential energy of the water inside of this bin here represents some energy, but it turns out that that energy was lost as well in this little door here in terms of heat because of the resistance to the water flowing through the door. And just as much energy was stored in this bin as was lost here. Okay? And again, Sam's son will show you how that works.
So no matter what the resistance is?
No matter what. If I made this door bigger,
exactly the same.
if I made this door bigger, right, it's some huge door, right? Pop it open, right? This is going to fill up much faster. So obviously the time that it takes to fill up will be much less. But guess what? The amplitude of the current will be much higher. And if you work out how much energy is lost across that door, even though the door is wider, it turns out to be the same in either case.
Would you say that's a coincidence? Or
No. That's a fundamental thing.
I guess you can calculate it and things, but that you come out with those two things being the same.
Yeah.
Why is which is a fundamental thing?
Well, here's another way to say it. It has to be true. Here's why it has to be true, okay? No, seriously, it absolutely has to be true. Let's think about the other case. Okay, I filled up my little sandcastle. Now the ocean dries up, okay? And there's no water left, right? And I have a potential energy stored in here. True? I now open a tiny little door, and a little stream goes out here, and this is the wide, wide world, so nothing ever builds up here. All the water goes out. Where does the energy go? There's only one place for it to go, which is to heat up the door. Okay, the resistance of the water going through here heats up the door. What if I make the door bigger? It'll happen faster. but the amount of energy I start out with is still the same. So it still has to heat up the door, and the number can't change. Okay, let's take a look at the diagram on the view graph here. We have a certain amount of energy, 1/2 CV squared, let's say, stored in the capacitor, because this guy's all charged up. And then we throw the switch to the other side, hooking this to ground. So the 1/2 CV squared is in here, and we know the resistor will discharge it all the way down to ground. Where's the energy go? It can only go into the resistor. Well, the situation where we're taking a capacitor and dragging it down to ground cannot fundamentally be different than taking the capacitor and charging it up. Those must be exactly symmetric things to do to it. Whether you're having the water go in to fill up or whether you're having the water go out to go down, it's the same thing. And so therefore the energy to charge it that's lost in the resistor, in the little door here, has to be exactly the same as the energy that's in here, because that's also the energy that we have to get rid of somehow when this thing is shorted down like so.
Say the same things and take away the door entirely.
So now you take away the door entirely. That's a great question. You take away the door entirely, and all of a sudden the water just goes, right, and goes out. Where did the energy go? Another way of thinking about it is charge a capacitor up and just short it out with a bar. Right? You get a really big spark, kapow, right? And where does the energy go? And the answer is a lot of it goes into heat. In that tiny little bit of door that's left, even though the door is like gone. You know, this is like asking, you know, what if you divide by 0, right? Then you get a very big number, okay?
Taking the limit.
Well, taking the limit, I bet you'll find the same number, okay? In electronics, it turns out that because the currents get so high, if you charge the capacitor and suddenly short it out, which you can do. I should have brought a demo here, plugged one into the wall and then gone bang like this. You get this huge spark, a huge amount of current, and what is not lost as heat will actually create an electromagnetic wave which propagates out, and that's another form that the energy can take. But
I wanted also the other direction. What happens if there's no door there and you're filling it up?
then it fills up instantaneously, right? Again, you're trying to take the limit of what happens as the resistance goes to 0.
Right. Where does the heat show up?
Well, it's one of those divide by 0 cases. So if you took the limit as it approaches that, you'll find that the numbers are still the same. Okay?
In the case of
You have to have conservation.
You have to have conservation of energy. The energy needs to go somewhere.
Potential energy versus kinetic energy
And
is total
so,
energy.
in that
Right.
case, the heat's going to be dissipated.
It has to go
through-
somewhere.
The energy's going to be dissipated through
Absolutely right.
It doesn't have to be lost as heat. When we open our gate, we could
Right.
put a turbine in there or
It's going to
something.
be,
and-
rather than lateral
have
flow.
to-
Ah, very, very smart. So why don't we put a turbine in the gate? If you don't put a turbine there, if you only have a resistor, then you will lose every cycle you charge and discharge this thing 1/2 CV squared plus 1/2 CV squared, which is CV squared worth of energy. Now, that happens every time you go through a cycle like this. In an inverter, there are 3 sources of power loss, okay, of energy loss. One is this phenomenon we talked about before called leakage. We said that no matter how good the insulators are over here, no matter how good this switch is and being off, when we say that the switch should be off, a little bit of current will get through. And what that means is that here's high voltage and here's ground, that when this switch is off and this switch is on, a trickle amount of current, some femtoamps of current, very, very small, will trickle through here, and some current will go directly from the plus 5 volts to ground. And that current times whatever the voltage is on the power supply will equal power that turns into heat. Tiny, tiny amount of heat. Now, in the old days of transistors that were like this, these were called bipolar transistors, the leakage was much higher. Okay, and some chips, statically, when they just sat there doing nothing at all but being in one state or the other, would actually get warm. Okay, the chips that are in the Commodore 64 there are like that. Okay, if you just stop the clock, they are still nice and toasty, okay, because of this leakage current. Field effect transistors we have these days are so good at turning off that that doesn't happen. The effect is there. It's not zero, but it's so low that it really doesn't make a difference.
And that was leakage that you just described?
Leakage. Second effect that happens is called shoot-through. Okay, really, really cool. Remember we talked about what happens when this input signal makes a transition from low to high. Let's say it takes a long time to make the transition from one to the other. What's supposed to happen when this is low, the top transistor is on. And when it's high, the bottom transistor is on. So we go from having this switch closed and this one open to this switch open and this one closed. But for a short time, both of the switches are closed. And they're kind of switching from being closed to open. And during the intermediate time, when the input voltage is halfway or near halfway between high and low, current will flow directly from the power supply straight down to ground. Now, how much current will flow? Not an infinite amount, a few microamps of current, because the devices, when the switch is on, still have some resistance. Okay, but during the transition, particularly if the transition is a really slow one, during this time here, if I feed this signal into that gate, during this time, the gate will have shoot-through. Current going straight down through both of the switches from the power supply to ground. And that will dissipate some of the power. But it turns out that in modern computers, these slopes are fast enough that that's not a dominant effect. But the last one is. The last one is capacitive charge and discharge. And what that is exactly what we just studied here. When that top transistor is on, it has to charge the capacitance of the next stage. And when the bottom transistor is on, it has to discharge the capacitance of the next stage. And so there's constantly these capacitors that we're filling up and draining out, and filling up and draining out. And the capacitance of the next stage is primarily the capacitance that's formed by the gates of the transistors of the next stage. Because if you remember, these gates are formed from a semiconductor of some sort, glass, which is an insulator, and then the channel. And that plate structure is the form of a capacitor. So, leakage, as I said, is insignificant. Crossover, shoot-through is relatively small if the rise times are fast, which is the case for most modern computers. And the capacitive one we just cannot get away from. We can't fix it by making the resistance of the devices lower. It's the capacitance that matters. We have to charge and discharge these things. Now here's an interesting question. If the amount of energy that those capacitors soak up every cycle of the computer is fixed, is a constant, then what is the power of that thing as a function of the frequency? The frequency is how often we do it. Well, a finite amount, a fixed amount of energy every cycle multiplied by the frequency of how often we do it will give us a power that's proportional to frequency. Now, how many people here have heard about overclocking your processor chip? Lots of you guys have thought of that. Okay. Well, you can do it. Okay. And in general, I talked about how what you're really doing is you're operating the device in a way sort of saying, okay, I'm assuming that the temperature will not get too high, and so it's okay to run this thing fast. But running the thing fast has a danger. The danger is that the faster you run your computer, the higher the amount of heat that it will dissipate will be. Because every clock cycle of the computer, a fixed number of joules of energy will be dissipated in the form of heat. And if you do too many of those per second, the temperature of the device will get hotter and hotter and hotter and hotter until maybe you burn the thing out. Okay, and that's no good. And so the reason that they warn you not to overclock your processor is exactly because of this. Because the faster you clock it, the hotter it's going to run. Okay.
How much can you overclock it before you get into trouble?
I don't understand overclock.
0. Overclocking means I buy a computer that is spec'd to run at 1 gigahertz. And it turns out there's a way of changing the configuration of the circuitry on the board. Usually you can do it through software and say, run the thing at 1.5 gigahertz. Okay, and it's running 50% faster than it should. And as a result, all of the capacitors on the inside are being charged and discharged instead of 1 billion times per second, which is still wicked fast. Okay, at least back in my days it was 1 million times a second. It was like way out there, So, and that was only 20 years ago. So, but now you're going to do it 1.5 billion times per second, and that will result in a 50% increase in general in power that is dissipated by the device. And when you have a device that can dissipate 10 watts, let's say, safely, and you say now dissipate 15 watts, it's like you're putting a torch with 5 more watts on the thing. It's going to get hotter. It'll reach an equilibrium point between itself and the air, but that point will be at a higher temperature than it was before when it was only dissipating 10 watts. And as a result, you may be over the threshold of where the silicon starts to get funny and melt and do all kinds of bad stuff. So, in general, the rule is that you want to keep the silicon of the device running usually less than 150 degrees centigrade. It differs depending on if it's a military chip or a chip made for us, but that's a good number in general to use.
That's still pretty hot.
Well, depends. You know, if you're on the surface of the sun, it's cold. So, there are other the other kinds of semiconductors that can run much more hot than that. So there's the capability of destroying the chip if you run it too hot. There's also the chance that as it gets hotter, things will go bad in terms of the computations that the thing does. Because in general, the propagation delay of silicon integrated circuits gets longer the hotter the chip is. And the reason for that is that the resistance of the transistors when they're on goes up the hotter they are. Okay? And so the RC time delay of trying to charge up the caps and discharge the caps gets longer and longer the hotter the chip is. So, okay. How do we minimize power loss? Does changing the on resistance of these transistors help? The answer is no. Don't get fooled by the fact that a resistor that has more resistance but the same amount of current going through it will dissipate more power. That's not the circuit we're talking about here. We're talking about a circuit where the actual current will change if the resistance changes in such a way that the energy dissipated will be the same. How about making the channel length shorter? What that means is making the distance between here and here, the length of the channel, shorter. Is that going to help? The answer is yes, but not because the resistance will go down. It's true that the shorter the channel, the lower resistance you'll have, and what that means is that you can make the chip run faster, because if the resistance is lower, the RC time is lower, and you don't have to wait as long to charge things up. Of course, if you want to take a bath in your house really quick, put in the 3-inch main going into the bathtub, and you'll be able to fill that thing up real quick. Okay, but it will not change how much energy is dissipated in the pipes doing it. It'll be the same as if you filled it up at a trickle. However, shortening the channel does help, not because the R changes, but because the C will change. The capacitance, remember, is formed by this being one plate of the capacitor, the glass in the middle being the insulator, and the channel being the other plate. And so the size of the bathtub will go down if we shorten the channel and make this less big. Yeah?
Do you get into more leakage problems as that gets smaller and smaller?
Absolutely true. You bet. Yeah. But usually the leakage here is so good that you don't need to worry quite so much. Mostly the length of the channel is limited by how accurate the photolithography can be to make the channel in the first place without shorting it out. Okay, so how about lowering the voltage? What if instead of filling up the bathtub the whole way, we only filled it up half the way? Would that be good? You bet. So lowering the voltage is great for two reasons. One is that it takes less time to fill up the bath halfway than it does to fill it up the whole way, right? So we can draw and drain more baths per second if we only fill them up halfway. The computer can run faster if we only insist that the voltages not go quite as far. And second, there's a lot less power that you need in order to go back and forth. And remember, it's 1/2 CV squared. So lowering the voltage can help a great deal.
Don't
Yeah.
capacitors, I mean, if you lower the voltage, then the capacitor fills up more slowly, correct? The voltage difference, so that your initial current is going to be lower.
It doesn't fill up more slowly if the power supply stays at the same voltage rating. In other words,
Okay.
if you still have 50 psi in your house, you turn the valve off halfway, then it is in fact faster. If the voltage on the input and the capacitor is the same, then the time will also still be the same. So RC says what the time constant is, independent of what the voltage is that you're trying to do. So whether or not you speed things up depends on the relationship between the power supply and what voltage you want the capacitor to get to. However, if you assume, which is a pretty good thing to do, that the voltages are the same, then the time will not change. Okay, except for a secondary effect that I'm just about to say here. Okay, so you sort of have two effects that fight each other. One is that you're not trying to go as far, and two, you have less pressure to do it with. Okay, and they actually cancel each other out, unless you take into account a second thing. Okay, so let's say we wanted to lower the voltage. Will the transistor still work? If everything here, instead of running on 5 volts, runs on 3.3 volts, will this transistor still turn on when this voltage is high? And the answer is that standard transistors have what's called a turn-on threshold. How high does this voltage need to be to turn this on? How low does this voltage need to be with respect to here to turn this one here on? And we can adjust, or doctor the channel is what it's called. We can put certain ions that get implanted inside the channel here to modify the threshold voltage at which the transistor turns on. Remember how the channel got made in the first place. If we put charge over here, it attracts carriers on this side to make a green line all the way across to create the channel from one side to the other and close the switch. If you have less voltage on the gate, the pull will be less. And so what you need to do is you need to modify the material in the channel here to make it so that it's closer to switching over from yellow to green, so that when the voltage, which is lower, does come on, it's easier to switch it to green. Yeah.
What happens if you have, if you're lowering it from like 5 volts to 2 volts? Wouldn't you have more metastability issues? Since it's, then how do you deal with that?
So it's absolutely correct that, remember, we had VOL and VIL and VOH and VIH. And there was this idea of a noise margin, which was the difference between the voltages on the input and the voltages on the output. The lower the voltages for the whole chip, the harder it becomes, in fact, to maintain decent noise margins throughout the chip, and the easier it is for you to get into that forbidden zone in the middle. And so you're absolutely right. And somebody else had asked the question, why can't you just lower the voltages down to 0.5 volts or 0.2 volts? And the answer is it becomes more and more difficult to tell whether you have a high or a low in a world of noise. And so if the noise isn't going to change, as the voltages get lower and lower and lower, it becomes harder and harder to tell the difference between the data and the noise. So yes, you're absolutely right. Yeah.
Does doctoring the channel increase the leakage?
Yes,
We're making it
it certainly does that too. Yeah, and so it's this whole trade-off where you're kind of playing this game of getting closer and closer to the edge of just about turning on the transistor at the same time that you're trying to lower these voltages. So it's hard to get these all right. Okay, so how about lowering R? If we lower R, then the circuit will be faster. So we can lower R in several different ways. One, as we said before, we can make the channel shorter, and that will make the resistance going through the channel less. And then the question is, from the top view, this is actually a side view. Here's the top view. Here's the gate, and here's one of the other parts of the transistor, the drain, and here's the source. And this is the gate that's going to let the current go through these both sides. Does making it wider in this dimension help? And you may think the answer is yes. You know, in other words, if this is a valve and the current is trying to get through from this side to this side, if I made this wider, then the resistance will go down. And that's true, because there will be more parallel paths for the current to get through from one side to the other. However, in the process of doing that, I have made the capacitance of this junction, which extends kind of out like this, I've made it bigger. And so if all the transistors are like this, I've made C go up just as much as I've made R go down. And this time constant RC is really the one that determines how fast the circuit will operate. Okay, so making the channels wider does not help. Then there's, of course, this question of how thick should the gate oxide be. This is beginning to get a little bit too deep for this class, but it's kind of fun to look at anyway. How much space should there be between the gate of that transistor and the substrate that is there? How thick should the glass be? And the answer is that the thicker that the gate is, the more voltage that you need in order to turn the transistor on, but the less capacitance you actually have in order to charge it up. Plates that are distant from each other have a capacitance which is less than plates that are closer. And so you may think that this is a way to speed up the chip too by making the gate oxide, the glass that's in between the gate and the rest of the transistor, thicker. And thus you lower the capacitance. But unfortunately, it takes higher voltage in order to turn the transistor on in that case. And so in general, this is not the right way to go, and gate oxides are made as thin as possible. In the old days was 100 angstroms. Okay, anybody remember what that is? An angstrom, 10 to the what meters? So that's 10 to the minus 10 meters. Okay, so that's pretty damn thin. Okay, the new ones are around 25 angstroms, okay, which are even thinner. Why can't they make them even thinner than that? There's a phenomenon called punch-through, which if this is the gate, and this is this incredibly thin piece of glass underneath it, incredibly thin, and here's the rest of the transistor that we've drawn here. If this oxide is very, very thin, first of all, you might make a mistake and the oxide might have a little hole in it here, which would cause this thing to short out to here, which would be bad. The second thing is that the ability of glass to withstand a voltage without breaking down, without getting a spark through here, depends on how thick the glass is. And how many of you know about the thing when you change a board in your computer, you're supposed to touch the case and not walk on the carpet and get static? There's a whole field called electrostatic discharge, ESD, having to do with handling parts that are inside of a computer. And sometimes they have these wrist straps that you put on and hook up to the ground and all this stuff. It's all because of these thin gates, these thin oxides. Because if, for some reason, now you know this is supposed to turn on at perhaps 1 volt, right? But if you go with your finger and you've walked across the carpet, or you've pet your cat, let's say, right, and you've built up some nice charge, right, and you go zap like this could go up to 1,000 volts. Well, 1,000 volts across 100 angstroms is many volts per meter, okay? And that's what an electric field is measured by, how many volts per meter of distance. And I don't remember what the number is for glass, but past a certain point, the glass will break down. Just like air breaks down and a spark goes through air, glass is good, but it's not that good. And it gets to a point, and then you burn a hole in the glass, and then the chip is forever bad, okay? So the limit to how thin you can make these things is both issues of ESD, that you want to make sure that when somebody, you know, has a bad hair day and their hair is standing up like this and they've got lots of charge on them and they go and they hit a key, right, that doesn't blow the thing up. That limits some of the sizes here. And also in manufacturing, I've actually had bad hair days like that. Also in manufacturing, there's always little pieces of dust and stuff like that get in the way when you make these things, and occasionally the thickness of this thing goes up and down. And so you have to make sure that at minimum it's not too thin and doesn't break through too.
What is the chemical substance?
It's SiO2, silicon dioxide, actually glass. Yep. Yep. Okay. So we keep trying to make our power lower and lower and lower and lower. How do we get rid of all this terrible thing with power consumption? And the one thing that I think you've all learned now is that the stuff that really eats up power is transitioning these capacitors from low to high and from high to low. So what if we changed our computer to minimize the number of transitions that are being made? And the answer is that often you can do that. Depending on the specific application that you're doing, oftentimes you can recode the data to minimize the number of bits that change. And there's a tremendous field now of learning how to do that, how to make the data that's flowing around in the computer change the bits as little as possible. Second, you can actually change the architecture, the way you encode a number, so that as the numbers change from one thing to the other for a typical program that is run, that you minimize the number of average transitions that are made. It's all trying to get to really the same thing. And then here's another thing that anybody that has a laptop knows goes on all the time, which is that there are parts of the computer which for long periods of time go unused, like for instance the floppy disk drive. So let's power that section of the chip down and not use that, and that way there will be no transitions going on there for a certain length of time. And then finally, there's the idea of putting the windmill, whoever thought of it out there, in the gate where the water goes by and recovering some of the energy that gets lost when you charge and discharge the system. And that's called reversible computing. And so this is what I want to talk about for the rest of the class here. And this is kind of wild stuff. So let's first of all ask ourselves a question, and this is really, really great. How little energy can be used to represent a bit? In other words, you know, I've told you it takes non-zero energy, but how little does it take? And then the second, regardless of storing a bit, is there minimum energy it takes to do a computation? Like we've just said that our capacitors have to get charged up and down as our computer runs. But, you know, why can't I build a computer that takes no power at all and figures something out? Is there something fundamental about computation, aside from memory, that says it should take power? Well, so here's the intuitive answers, which are actually both wrong. It can take arbitrarily little energy to represent one bit. That seems like that should be true, but it ain't true. And the second one, which is even more wild, is computation must consume power. In other words, my computer needs to be plugged in. And the answer is, well, that's actually not true. It's theoretically possible to compute with zero power. And that answer was actually only figured out in the 1970s, which is kind of wild. Okay, so let's take a look at the smallest amount of energy it could take to represent a bit. And it turns out that if you study physics, you find out that the simplest information system that there is a particle of gas that's bouncing around in between two ends of a box. So here's the particle of gas, and we have two pistons, one on each side of a cylinder, and it's bouncing around in here, okay? It's only one particle. And what is the kinetic energy of the particle? And this actually teaches you something really, really cool, because the kinetic energy of that particle is T, where T is the temperature of the particle. And in fact, what temperature is a measure of is the average kinetic energy of things, of the gas. So if gas is moving around in the air, the average kinetic energy of the gas is going to be T. And T here is the absolute temperature. Okay? Well, that's cool. But what if I wanted to store a bit in this system? And it turns out this is the most simple system I can build to actually store a bit. What I need to do is I need to take this piston on the right, I need to squeeze the particle over to the left, and I need to force the particle to be on the left-hand side. Because the simplest representation of a bit that I can think of, that anyone has been able to think of, is if I have a particle that previously could be anywhere, either on the left or on the right, and I now constrain it to being on the left, I have created one bit of storage. Okay? And I challenge all of you to think about any other way to store a bit. And I think that you will never be able to come up with one that is more simple or that represents less energy than this. Okay, now, everybody here, I think, should know that if you have a fixed amount of gas and you squeeze it in a piston, it takes work to do that, right? You have to go, and you squeeze it down, right? You compress the gas. And what's interesting about that is, where does the energy go? Well, anyone who has played around with having an air compressor knows that the air compressor will compress the air and you'll end up getting hot air, right? It'll all get hot. But let's assume that we have this big heat sink over here that will take away all the heat. In other words, we hook this up to, you know, a big liquid bath that's at the same temperature we started out with. And so as a result, when we squeeze this gas, we're not going to worry about the temperature changing. The temperature is going to stay exactly the same. What that means is that the kinetic energy of the particle, the speed of the particle bouncing around in here, will not have changed. So we start out with a temperature T, and we end with the same temperature T, just so that we don't get confused between heating up the gas by squeezing it and forming the bit by constraining it to the left-hand side.
Sorry, why do you say that again? That, like, because when you pull a piston, I guess, once bounce off there, you think?
Well, there are, okay, in general, in these thermodynamic systems, there's two extreme ways to do it. Okay, one is called the isokinetic case, which is what we're going to do, and the other one is the isothermal case. Did I get that right? No, I am wrong. One is the adiabatic case, which is not what we're doing, and the other one is the isothermal case, which is what we're doing. Thanks. In one case, you hold the temperature fixed, and in the other case, by hooking up a heat bath. In the other case, you hold the system fixed by not allowing any heat to get out. Okay? We're going to drain all of the extra heat out of the system. So we're going to keep the temperature fixed as we squeeze the thing. Okay? So we've squeezed this particle over to the left-hand side. Now the question is, did it take any energy to do that? The speed has not changed. Did it take energy to do it? And the answer is yeah, it sure did. Because whatever the pressure of that gas was when I was over here on the right, now where did the pressure of the gas come from? The particle's bouncing around, and every once in a while it bangs into the piston. Bang, bang, and kind of pushes me. It wants to get out, okay? So it's giving me a force. And that force times the distance, which doesn't change, by the way. As I go to the left here, it still hits me with the same force, okay? As I go to the left here, the force times the distance is the amount of work that I do squeezing this guy over to the left-hand side. Okay? And that's the energy of creating one bit in the minimum possible system, putting this guy over to the left. So the kinetic energy of the particle is not any different, and it does take energy to move it over to the left-hand side. And we knew that it took energy because the particle was bouncing against the piston. And where did the energy go? When we're all done, where did it go? It went into two places, and it turns out an equal amount of energy, and this should sound like a familiar thing, went into each of the places. First of all, the particle wanted to get faster because we were squeezing it over to the left. Had less space to bounce in, and we actually gave it a little bit of a kick when we were pushing over on the left. Well, we drained away the extra heat in the heat sink, so half of the energy went there. And the other half of the energy went into the information that it's on the left and not on the right, or that it's on the left and not possibly in either of the two places. We created order where there was disorder before. There was disorder in that we didn't know which side it was on, and then we pushed the particle over to the left and we said, okay, you're on the left. And that actually took energy to do. And that energy went into ordering the system. Yeah?
Doesn't look like it would take energy, though, now that you've got it compressed, to scoot both pistons over and change the state of the information.
Brilliant. It doesn't. It doesn't. And we're going to talk about that too. Okay, we've created one bit of energy, and if you're a physicist and you go through the calculation, you'll actually discover that the amount of energy that it took to squeeze that particle over to the left-hand side was log, or it's actually ln of 2, log base e of 2, times kt, where k is the Boltzmann's constant. Okay, very small number, and T is the temperature of the system. So we typically talk about KT as being the amount of energy, but it's actually log base 2.71828 of 2, which is pretty close to 1. And it's 2 because there were two states in the system.
I'm sorry, the logarithm
Is base E.
is of the...
Is the natural log of the constant 2.
So why don't you just incorporate it into K?
I could, but K is a physical constant of Boltzmann's constant.
Where does K come from?
It's a fundamental constant of the universe.
Okay.
And that's as good as I can do. Okay? There are some people that actually says there are some people that actually say that K comes from this. Okay? That in other words, the reason K is what it is because of this factor here. That when you try to create one bit of information, it takes log base E of 2 kt energy to do it. But there are many places where you see K come up. Anyway.
So this energy is the total energy, which is part information and part heat.
This is only the information part.
So this would be the minimum amount of energy.
The minimum amount of energy that you could possibly use. Right. So if we got rid of the heat sink that is what it would take. Yeah.
You could get rid of not making heat at all, say
Right.
doing it very slowly or something.
Ah,
like
right.
That would be the minimum energy.
Yes.
Temperature's gotta be in Kelvin then, right?
In Kelvin, yeah. So it's 270, something. Yeah. It's room temperature. Okay, can we get the energy back? The answer, the great answer, is yes. In the same way that it took work to squeeze this particle over to the left-hand side, work can be done on me pushing this particle back. Okay, if we do it slowly. Okay, if we do it fast, then everything gets screwed up because we are trying to extract, let's see the right way to say this thing. If I fill up the bathtub, okay, and instead of using a half-inch pipe, I use a turbine, then I can extract, and I fill up the bathtub very, very slowly so that the amount of energy dissipated by the piping that I still must have is very low, then theoretically the turbine can give me all of the energy that formerly would have been lost in the piping. However, if I try to do it too quickly, the remaining piping that's still there will still dissipate some of the power. So as long as the computer is running slowly enough, it is theoretically possible to recover the energy of storing a bit of information in the charge on a capacitor and recovering it by discharging the capacitor as well. But we need to put something between the capacitor and ground other than a resistor. We need to figure out the equivalent of a turbine to put in that stream. So kind of wild. And in the same way, if we can recover the energy like this and then put the energy back in, squeezing over to the right, then it must also be true that we can move both of the pistons to the left and the right without doing any work at all, which is true.
Changing information.
Well, are we really? We're telling whatever state the system was in, switch it to the reverse state. Are we really changing the information? If I said, if your shirt is white, change it to black, but if your shirt is black, change it to white, I still have one bit of information as to what your shirt was before we started. All I'm doing is changing the polarity, which itself is a computation that preserves the information that we had before and does not create any new information, nor does it destroy the information we used to have before. And it turns out that is the key to building computers that require no power to run.
So what does
Yeah.
slowly mean here?
Slowly means slowly. In an electrical circuit, what it means is if you look at the RC time constants of the resistors and the capacitors, that you operate perhaps 5 to 10 times slower than those time constants. And I'll show you in a second. What does it mean with this thing here? I don't know. Okay, it has something to do with how fast you move the piston compared to how fast the temperature goes in and out of the heatsink.
This is the idea of these hybrid cars that are legal.
Has nothing to do with the hybrid cars. No, I have worked on those too, but that's a totally separate thing.
Well, you're recovering energy though.
Oh, you're talking about the regeneration when you brake. Ah, yeah, it is the same. You're absolutely right. So the kinetic energy that you usually have in your car when you speed up. Oh, this is actually a great example. Wow, thank you. This is wonderful. Okay, so let's say that your engine were 100% efficient, right? And you used your engine to get up to a certain speed. And you took so much energy in order to do that. And then you hit the brakes. If you have standard friction brakes, the energy you used to get up to that speed would then be dissipated in heat in the brakes, right? Now, the systems we've been talking about up till now have it even worse. They have a resistor, a clutch, between the engine and the car. The engine's always going at the same speed, and the way you know how some folks drive, right? A standard, they get the engine up to full speed, and then they slowly let the clutch out, right? And the clutch goes, and then the car gets up to speed, right? I have friends who drive like that. And the clutch gets hot, just like the resistor between a power supply and a capacitor gets hot. The momentum of the car, the weight of the car, is like the capacitor, and getting it up to speed is like charging the capacitor up to a certain voltage. And if the engine's going at 3,000 revolutions per minute and you slowly let the clutch out, then the clutch will get warm And it turns out the amount of energy you will dissipate in that clutch is equal to the amount of energy you will give to the car to get it up to full speed, the kinetic energy of the car. And then when you hit the brakes, that energy will be dissipated in the brakes. And that's what we've been talking about with these RC systems. On the other hand, in an electric car with regenerative braking, when you hit the brakes, it does an incredible thing, which is it converts the electric motor, which got the car up to speed to begin with, without a clutch, into a generator and puts some of that energy back into the battery of the car. And in fact, it works exactly the same way as what we're talking about doing here. So yes. A hybrid car also has a gas engine too, which has nothing to do with it. So, okay.
So does this system require initial energy? I mean, you're then sort of passing the same
Yeah.
energy back and forth, but you can't just start with nothing.
Absolutely true. But what we're asking is, does it take power to run a system, not should I charge it up to sort of start with? Okay, so in summary, slow, reversible thermodynamic processes can recover the energy put into creating a bit. If you go too fast, you tend to lose it in the resistance of the wires. You can recover an arbitrary fraction of that energy by going slowly enough. And it turns out that whether you do it the isothermal way or the adiabatic way, where you have an insulator between the cylinder and the rest of the world, doesn't make a difference. You can do the math for both cases. It's actually the speed that matters. You need to go slowly enough to recover the energy. And that's energy storage. How about computing? Well, computing means that we're going to create a new bit of storage whose value is determined by looking at other bits. So computing and memory are intimately coupled with each other, where computing is just a functional transform from one set of bits of storage to a new set of bits of storage. And here's the question. Looking at the bits is free. We don't need power to do that. It's when we create or destroy bits that we need energy. Let's see if I can make sure that you guys believe all of that. It's the storage of the bits that takes energy. If I take a bit and I destroy it, what I've basically done is I've drained away the energy that I put into the bit in the first place. And so it's when I destroy a bit that power gets dissipated. If my computation can be done in such a way that bits are never destroyed, then what does it mean? I can theoretically recover all the energy to begin with. Now let me ask you a question. I have a computation which is going to calculate the factorial of a number. Okay? So I put in, n is 6. What is fact of 6? Does anybody know offhand? 720. You guys have been doing fact a long time, right? Okay, let me ask you a question. This obviously has more bits than 6 does, right? But how about bits of information? Is there more information if you know that you're doing fact? Is there more information in the answer than in the input? No, because one completely determines the other. So in fact, this computation, if I know I'm doing fact, the computation is reversible. Okay, let me ask another question.
How many bits does it take for you to know you?
Well, there's a finite number of bits to do fact. I just look at the text of the code to do fact. And so
I guess somehow it cannot be less.
here's what I'm trying to say. If I do fact over and over and over again, does it take power to do it? Not, if I do it once. Right? It's always easy to fool yourself if you do these things just once. But in the limit, as you do them forever, the overhead of knowing what fact is kind of gets lost. Okay? The question is the computation itself one that consumes energy every time? And the answer is, in a standard computer, yes. But theoretically, it shouldn't have to, because we have neither created nor destroyed information between the input of fact and the output of fact.
Can't we just make a table and read the table?
We could do that too, sure. Sure. But we don't have to. We could have fact as a program that we don't know what n is to start with. And what I'm just trying to say is that the execution of the program fact does not need to consume energy, because whatever energy it takes to figure out the answer, I can get back by reversing it. In other words, if I had to create 12 extra bits here, let's say, in order to represent the number here, I could then go, and knowing that I want to get back to 6, I could soak up the energy of all those extra bits and get all the energy back by
Provided you
reversing
wanted
the
to go back to
computation.
6. What if you wanted to use fact for something else? Then
Ah, good. What about greater than? Okay, I give it two numbers, A and B, and it gives me one out, A. Trouble. Why? Because greater than is not reversible. Right? It destroys the information of one of the two, and I only get one. And that destruction will just dissipate the energy. Unless I'm very smart, and I say, well, you know what? I'm going to keep around both of the inputs. Okay? And so the output of A and B, after the greater than program runs on it, will be three things: A and B, and whether A was bigger than B. And this computation, if I know it was greater than, can be reversed in order to get back the energy that I used to create this middle answer right here. And it turns out that every computation, by carrying along enough of the inputs, can be reversed. And it is actually possible to build computers that, as they run forward, they never destroy the information that they have. They always carry along copies of the inputs, sufficient so that you could hit the button, this computer doesn't have it, between forward and reverse, and run the computer backwards, and whatever energy we had to put into the computer to come up with the answer would go back into the battery as it reversed and got back to the input. And so in general, what reversible computers do is that they have a direction switch on them to run forward or backwards.
Are these entirely theoretical, or
No, people have
they
built them.
actually
Yep.
exist?
I supervise, I guess, 2 different students along with some other folks who've actually built these. I'll give you a reference at the end. And typically what is done is you run them forward for a while, you make a copy of the answer. Now that represents some energy loss. Okay? But it's not the energy loss of all the computations that were done. It doesn't matter how much thinking this needed to do in order to come up with the answer. You get a fixed amount of energy from the answer, and then you run it backwards and you undo all the work that it did, and you end up with 0 power. It takes twice as long to do anything because you have to run it backwards, but you can run it at 0 power. And that's an incredible thing.
To get from N to 720.
Right, and then you get the power back
How
out.
do you get it back?
Well, I'll show you. It works just like those cars. Okay? So in the standard inverter, we have power supply rails at a fixed voltage. Just like the brake pedals. This is really good that you gave me this. The brake pedal in your car has brake pads that are fixed to the car. They're at 0 speed, and they brake to the car. On the other hand, you could have a flywheel, for instance, and some kind of automatic transmission mechanism in order to slow the car down by extracting the energy in the wheels and spinning up some flywheel at the same time. And at the end, when you came to a stop, the flywheel would be going at some speed and you'd have some energy there. Or you can use the motor as a generator and you could charge the battery as you slow down. This thing works the same way. This is very fast, but as we saw before, because it's fixed resistors when these are on back and forth, this is a non-reversible type of gate, and it throws away lots of energy. What we're going to do is we're going to do something a little different. There's a lot of text here, so I'm going to do it on the picture. Let me see if we do it here. Here. Instead of having these 2 rails at 5 volts and ground, we're going to start out with these 2 rails at a common voltage in the middle, 2.5 volts. Okay? And we're going to decide, do we want to create a 0 or a 1? And we're going to close either the top switch or the bottom switch. And then we're going to very slowly let the voltages on the top and the bottom go from 2.5 volts up to 5 volts. Very, very slowly. And this turned on switch will slowly charge the capacitor, but it will charge it in a recoverable way without allowing the resistance to ever get in the way. So maybe I can draw it over here a little better. Let's say instead of trying to fill up here's our little door. Okay, before what we did is we had this one empty. We opened the door, and the water rushed into it, and we kept this thing at the same level. What we're going to do now is we're going to say we're going to do it a new way. Okay? We're going to start with the water down here, and the water here is down here. And we're going to open the door. And I'm going to very slowly raise this thing up. And the water here is going to go up with it. And I'm going to very, very slowly raise the water up a little bit at a time. And I'm going to do it in such a way that the rate of flow through the door is always very, very small. And it turns out that the slower I do it, the less total energy is lost going across the door. So that by the time this thing gets up to the top, and this is up to the top, if I do it sufficiently slowly, the amount of energy that I lose going through the door can get arbitrarily small. And then I can descend this the same way. Now, I still haven't solved the problem of somehow I need this to go up and down. Okay, but the way that that's done is that the power supply of the chip, instead of being a DC value, is actually made to be an AC value. It goes up and down and up and down and up and down. The voltage, instead of being just 5 volts, is an AC, typically a sine wave that looks like this. Or sometimes it's a half sine wave that looks like that. But it starts at a mid value and it slowly goes up and then it goes back down and slowly goes up and it goes back down. And the transistors are all switched when the voltage between the positive rail and the negative rail is 0, like right here. And that's the same as saying that I'm not going to change the door from open to closed until the levels are the same. And I'm going to raise and lower the levels here slowly enough so that I will dissipate no net or as little net energy across the door as I possibly can. And this actually works. Okay? And to give you a diagram of a circuit that actually does it, I'll show you this one here. And this is this guy named Tom Knight who did most of the stuff, and here's how it works.
When did he do this? Is this like really recent, or is this?
This particular one is maybe 4 years ago or so. Some other ideas for how to do this came from a fellow named Jack Dennis in the 1980s. But the most recent stuff is 1990s. Here's how it works. The power supplies are these blue lines. In this circuit, power and clock are the same thing. In other words, the power goes up and down and up and down and up and down and up and down. And so the way to think about how this thing works is that these two signals here have a voltage that goes together and then apart, together and then apart, together and then apart. And what this selector is going to do is, depending on its control input here, it's going to choose to either hook the positive power/clock line or the negative power/clock line up to a capacitor right here. And very slowly, after it closes the switch here and chooses to go up here, this clock will go from low to high. And it'll do it slowly enough so that the resistance along the path does not dissipate very much energy. Once that's done, that will in turn control another selector, which on a later clock, this will at a later time go from low to high. That will in turn cause this capacitor here to get charged from a 0 to a 1. And that gets fed back here. And notice that this is a positive feedback loop, like two inverters coupled to each other in a row. And this over here is a memory storage element in what's called a reversible logic family. In this case, it's SCRL. It stands for split something rail logic. I don't know what the C is, but split rail logic. Now, you don't need to, of course, know the details of how this thing works, but I wanted to show it to you as an example of how it might work. And again, the idea is that you never close a switch, you never connect a resistor across a voltage difference, like connecting it between the power supply and the capacitor directly. What you do instead is that you lower the power supply down to the value that the capacitor has, you close the switch, and then you slowly raise the capacitor value up. And as a result, the resistance doesn't dissipate very much. The energy ends up going back into the system that generated the power in the first place.
Is this a commercial product?
I don't know if it's quite made it that far yet, but they actually did build chips with this stuff.
What kind of clock speed, I mean, how much slower would this be than?
So it's roughly a factor of 10 slower than what you would buy a system.
So it'd be perfect for PDAs.
For a PDA, for a watch, for things like that. So I think I've actually already gone through this with you about how we should go backwards in the computation in order to recover the energy. Here's some answers. How little energy can be used to represent a bit? Well, we learned that kT log base E of 2 is the minimum energy. By contrast, a CMOS gate in a computer uses 10 to the 8th times more energy. Okay, so that gives you an idea of how much more we use to represent a bit in the Pentium than theoretically could be used. So we have many, many years to go before we get down to the fundamental limit. Of course, as we scale down the size of the parts, the capacitance that we use goes down. As we scale the voltage down, the 1/2 CV squared goes down as well. So the energy is going down, but we're still at 10 to the 8th. What's amazing is that to duplicate a single bit of RNA uses 100 kT. So even there is 100 times more, but it's a heck of a lot less than 10 to the 8th. So nature has us beat, okay, by a long shot. And as you know, computation does not need to consume power as long as it is done reversibly and sufficiently slowly. And that's the stuff behind the work that they've done at MIT. But what's also an amazing thing is that when we're all sitting around, if we're not sleeping, our brains consume around 40 watts of power, which is not very much. A 40-watt light bulb, you know. That's I think when you lecture, it takes a little more. But, and hopefully when you listen, it takes a little more, too. But there are 10 to the 10th neurons, I think, in the brain. And when you think about how much power each one is using, it's very, very little. So, okay, here's places to go. There's a book called The Feynman Lectures on Computation, which basically give the lecture that I just gave plus a little bit more. You can look at these websites, which is really cool, and you can also buy this book or try to get a hold of this book, and it'll talk about the thermodynamics of computation, which is a pretty neat thing to do. So that's the story.